Hello everyone, my name is Val and today I'm joined by my colleagues from the University of Glasgow. We'll be appearing in person this June at the Glasgow Science Festival to show off our research. We'll have 4 hands-on and 1 visual demonstration for kids and perhaps some adults to get involved with. Our theme is Our Sun, the Dynamo. It's about our research that we do here. And there'll be stuff that's interesting even for the massive plasma physics experts that I'm sure are going to be watching this video.
Hi, I'm Francesca. I'm a PhD student at the University of Glasgow and I model the Earth's dynamo. Here we have a plasma ball and our sun is made of plasma. It gives off light just like our sun and it's also very chaotic just like our sun.
Hi, I'm Luke and I'm a postdoc here at the University of Glasgow and I research the generation of the magnetic field inside the Earth. I'm here to show you a demonstration which uses iron filings to show, give this a shake, show the magnetic field lines around this bar magnet. You can see that the lines go from one end of this bar magnet, the North Pole, to the south. The Sun is also a giant magnet and emits a steady stream of particles into the vacuum of space. We can use these particles to show the magnetic field lines of the Sun.
Hi, this is Aisha Server, a PhD student working in dynamo simulations, and our next theme is that Sun is full of electromagnetic forces. So if you would visit us, you would be able to assemble an electric motor from a few simple steps. So we have 2 magnets and which are around the armature, and the armature has a current carrying wire which goes multiple times around it. So the current is such that it is perpendicular to the magnetic field, that then we have force on both of the sides of the armature. So this is how Sun works. So there are currents that flow past the magnetic field, and then we have huge forces that launch out the plasma loops that are even larger than the entire Earth.
Hi, I'm Francis, a PhD student here at Glasgow, and I'm currently studying the onset of convection in structures within dynamo. Here I have a toy dynamo which, on rotating, spinning this wheel, we can cause current to pass through the circuit, turning on the diode. However, if I rotate the wheel in the other direction, the diode does not light up as the current passes in the other direction. To get around this, we can flip the polarity of the magnetic field. And now, if I rotate in the anti-clockwise direction again, the diode does turn on. The core of the Sun is extremely hot, and this is where we see nuclear fusion reactions occurring. Outside of this, we have a vacuum of space and then a colder boundary. This hot and cold boundary then allows convection to occur. These sorts of circular motions then can move around the electrical conducting plasma, the ionized gas, and then can cause these currents to form, as we've just seen in the toy dynamo. This can sustain and can create a magnetic field, which then we can see outside of the Sun in the form of coronal loops, for example. I know you have a feel for what we study here at Glasgow. The Sun has a magnetic field, which then, because the plasma is ionized and is conducting, we see convection due to the hot and cold boundary. This hot and cold boundary then creates the convection, which generates currents, and these currents can then enhance a magnetic field structure again, completing this cycle.
Hello, my name is Sage Danish. I'm a PhD student at the University of Glasgow, and I study plasma in motion. So, you've seen a couple different demonstrations of how the electromagnetic forces can interact to induce motion. In this case, we'll see how they can induce motion in a fluid. We just saw the example of an electric motor, where you have an electric force and a magnetic field at right angles to one another that cause a motor to spin. In this case, we'll use that same force to pump water. What we have here is an MHD pump. We have a series of metal slats along the pump that are connected with a copper wire. This we will run a current through, so we'll have an electric field that runs this way. We also have a series of magnets on the top and bottom of this pump that induces a magnetic field vertically. So this electric field and magnetic field are at right angles to one another, and if we immerse this in salt water, which is a conductor, it'll pull the water through these channels out towards you. And hopefully you'll be able to see this in our demonstration. So, as we've just seen, using electromagnetic fields, we can pump fluid around. Now, the surface of the sun is composed of a plasma. This is a very strongly conducting fluid, and it turns out that if we have the right configuration of electromagnetic fields, i.e. ones that are at right angles to one another, we can eject large amounts of plasma from the surface of the sun out into space. And that's what I study.
So we'll be around this June, 8th and 9th of June, at the Riverside Museum, Glasgow, if you want to come and chat to us about plasma physics, astrophysics, and all things sciencey. Hope to see you there.